Hello, everyone, and welcome to Virtualizing High-Performance Computing to Advance Science Research, a roundtable discussion presented by EMC. I'm Morgan Edwards-McGee, Operations Manager of Life Sciences at Fierce Markets, and I'll be moderating the webinar today. Our speakers are Sasha Pagel, Business Development Manager for Life Sciences at EMC, and Josh Simons, Office of the CTO at VMware. You can read their full bios on the right side of your window. So just a few technical notes before we begin. If you have trouble reading a slide, please hold and drag the right corner of the slide window to enlarge. Please also disable your pop-up blocker to participate in the interactive parts of the presentations. To download a copy of the slides, please click the Download Slide widget at the bottom of your screen. We'll be following the presentations with a Q&A session, so please submit your questions during or after the presentations using the Q&A box at the right side of your window. I think we're ready to begin. Sasha, please take it away.
All right, thanks. Hi, everybody. This is Sasha Pagel, and I'm the Business Development Manager for the Life Sciences here at EMC, and I actually work in a really specialized team where we have an explicit focus on different industries, and in my case, my team members and I, we live and breathe, anything and everything related to life sciences and genomics. And so that means, working directly with customers in terms of collaborations, also with technology partners like VMware, and then also, working with our teams here to ensure that, everybody has a solid idea of what's possible in the respective environments in terms of EMC technologies and life science workflows. Usually, when I open these webinars, typically we start out talking about storage and how that fits into the world of life sciences, and that really, I think more recently, it's more important to just kind of look at what is it that groups are looking at, and how are they rethinking, their current architectures or models for storage and computing. Many of you may have already heard the recent announcement, I think as of yesterday, from Complete Genomics. They announced a competing solution to the Illumina X10, and they claim they can, produce, 30,000 whole genome sequences in a given year. And if you translate that into storage terms, that's approximately say 3 petabytes of data. And so that really does motivate groups not just to think about how data is immediately stored, but you really have to think about the life cycle of the data, and then also different approaches in terms of how to compute and analyze that data. And where we really started this webinar series was really to look at new modes of thinking in terms of managing the entire life cycle. And so some of you may have attended the first session where we described work with the IRODS consortium and how different groups can take advantage of IRODS to really be that piece to mediate the life cycle of genomics data, both in terms of active use of that data and also just long-term preservation. A couple weeks ago, we had another webinar really more focused on how to address long-running different types of analysis pipelines, variant calling pipelines, and we highlighted, sort of new and emerging methods like Atom, which take advantage of Spark, and these are methods coming out of the Berkeley AMP Lab, for example. And that was really focused on different methodologies, and now kind of to sort of cap off this webinar series, really taking a look at different approaches in terms of computing on data and making computing available. I had the privilege to meet Josh last year at Supercomputing and learned a bit what VMware is doing in terms of virtual HPC, and he definitely clarified some perceptions of my own in terms of what virtual HPC is capable of in the latest work from VMware. So I thought it would be appropriate to invite Josh in and have a discussion, have him share kind of the latest and greatest about virtual HPC, and hopefully get everybody up to speed in terms of what the possibilities are when it comes to virtual HPC, and especially in terms of scientific computing or genomics computing. So with that, I'd like to introduce and have Josh take it away.
Thanks a lot, Sasha. So as you said, the topic here is virtualizing high-performance computing, or using virtualization and cloud technologies for high-performance computing. And the tack I want to take here is perhaps a little bit different than people might think. I've found that it's often the case that the HPC community, when they think about cloud at all, they tend to think about public cloud. But in fact, I think there have been studies that show that the intensity of usage of physical HPC resources or compute resources within HPC are so intensive, really often a 24/7 kind of environment, that moving those sorts of computational workloads wholly into a public cloud is really not economically the right thing to do. So the net result of that is that there will continue to be, for a very long time, significant amounts of on-premise resources that are used for HPC. And so what we've really been looking at VMware primarily is the use of private cloud technology in essentially a layer that you would put on top of a bare metal HPC cluster in order to deliver certain capabilities. And so to sort of motivate the discussion today, I'd like to start with this particular scenario. And this is a scenario that we find to be very common among a lot of the institutions that we speak with. And so the idea here is we've got an organization that has these, what I'm calling, isolated islands of compute. So these are clusters, and the blue boxes are meant to denote individual machines in a cluster. And then the colored bar above that is meant to indicate that there's some kind of an OS distribution that's been layered across that cluster. So it might be CentOS, it could be SUSE, Ubuntu, Windows in some cases, et cetera. And the reason that we get here is often the case that PIs have gone off and received grants. Those grants include funding for equipment, and then the equipment gets spun up within the particular department that the particular researcher is working on, or a particular project, and you end up with these disparate islands. There's a desire in a lot of these organizations to bring these together into a centralized compute environment. And in particular, so the idea would be to aggregate the resources together. Now, there are some barriers to that. The most obvious one is the fact that you're running different software environments across these different islands. And so the question would be, if you went in this direction, what would you actually decide to use as a distro here? Because you're not going to be able to satisfy everyone's requirements. It maybe perhaps goes without saying that in a traditional HPC bare metal environment, this really is a single choice. These are homogeneous clusters that are set up to serve the population, and that is somewhat of a limiting approach. So what we are looking at, and what seems to be resonating a lot with customers, is this idea of, rather than layering an operating system down across that entire cluster, put a virtualization layer there instead, so a hypervisor or a kernel that offers virtualization capabilities. Once you do that, it's now possible to bring all of those disparate workloads together at the same time onto that infrastructure. So you're able to create by using this virtualization layer, you're able to create a heterogeneous environment that essentially offers a bring-your-own-software stack approach to compute. So people with their Ubuntu, people with Red Hat, et cetera, can all come together and take advantage of these resources simultaneously. Now, if we do a deeper sort of drill down and look at one individual node within the system, within that cluster. So we've got the hardware that I mentioned before. You see that there's a hypervisor here. And then there's the virtual machine abstraction that is represented by the green rectangle. Within that, an operating system runs, and then within that, we have applications that are running. So what you see here are three different operating systems, three different kinds of operating systems running at the same time on this individual piece of hardware, and with an application running within each of them. Now, you contrast that to the situation in the bare metal cluster environment where you're using some kind of a batch scheduler. You're running a Linux instance of some sort, usually, and then you're running multiple jobs within that individual operating system instance. So now if we look at the kinds of benefits that you accrue when you move to a virtualized approach to standing up this infrastructure, There are several of them, and I'd like to go through these in turn. So the first one we've already talked about is heterogeneity, this idea that you can bring multiple software stacks onto this physical cluster at the same time and do that very dynamically. The second one, which is especially important in the life sciences space, is the ability to have this virtual machine abstraction act as a security barrier between your jobs. So for example, if you have a set of researchers who are working on, say, clinical data that absolutely must not leak out even to other projects that are running simultaneously on the same machines, then the virtual machine abstraction can help with that. And similarly, there could be a secure connection from an individual virtual machine, say, to an Isilon storage system that's allowing that full isolation of the workload to restricting it to use just by the people that are authorized to take advantage of it, while at the same time allowing you to make very effective use of the underlying hardware infrastructure. Right? If we couldn't bring all the resources, all the different researchers together onto the same hardware, we would potentially have the situation where we're not necessarily, say, using all the cores in the system. So the ability to pack them in and have protection is really important. There's also this issue of fault isolation. If you think about what's going on the left-hand side in the bare metal environment, failures in one of those jobs or applications, say at fill/temp on that in that OS instance, for example, have the potential to either slow down or disrupt applications that may be running on behalf of other users. So again, putting these applications into their separate virtual machine containers gives you an ability to have fault isolation. There's also the issue of reproducibility, which is coming up more and more in the news today. I just saw an article about this actually this morning, about the fact that it is becoming increasingly important to be able to fully reproduce the research that's being done here. And we of course can't claim that everything we offer on the IT side is going to fix that problem, but the ability to take a snapshot of this virtual machine and the entire state of the application and the operating system running within it is one very effective way of completely saving away the state. Essentially, it's an audit of what was done to produce the research. And so this is a built-in capability in the platform that really just comes for free. There's also fault resiliency, so this idea that we can use this snapshotting capability not just for reproducibility, but we can also use it for saving aside the state of the machine and the application in case there are underlying hardware failures. Right, so the idea of doing a checkpoint, but doing that in a way that is much more seamless and complete than is possible in a bare metal environment. And then also a very important thing is this idea of dynamic load balancing. So in standard HPC environments, it's really a very static realm from a job placement perspective, in the sense that when you're using a batch scheduler, that batch scheduler makes the best decisions it can based on the current layout of the workload on the cluster. But once it places a job, that job sits there until it either completes or you kill it or it dies. In a virtualized environment, we have the ability through a technique called live migration to actually move individual virtual machines around between physical machines in the cluster, and do that without really disturbing what's running inside that virtual machine. So the operating system continues to run, and even the application within it continues to run. So by having dynamic load balancing, we have the potential to make better use of the overall available hardware resources in the cluster by doing a better job of packing applications and jobs into the hardware infrastructure. And then the last one, which is somewhat counterintuitive, is that we sometimes can offer better performance in a virtual environment than you typically see in bare metal. And I should have said this at the beginning. I will talk a lot about performance as we get a little bit further into this, so have no fear. We'll get to that. Okay, so those are the main uses of a virtual machine. Now, if we back up and think about this virtualized infrastructure that I was talking about, and then add, sort of bookend it with management and monitoring, this is a very viable way of using virtualized infrastructure. And I think of this as being really sort of admin. It's mediated by the administrator, in the sense that the model would be a researcher comes to the administrator and says, I need a 12-node cluster. the administrator turns around and very quickly, using the virtualization management capabilities, spins up a 12-node cluster that's actually 12 virtual machines, hands that back to the researcher, and then the researcher goes off and does with it, whatever they want to do with those 12 nodes, presumably running it as some kind of a virtual cluster. But we can go a level higher in abstraction, and we can add a private cloud layer on top of this. And what that does is it removes the administrator from that flow and gives the ability to the end researcher to self-provision either individual virtual machines or potentially even clusters of machines, including, say, Hadoop clusters. The idea being that and they can do that from predefined sets of templates. So the IT organization and the researchers sit down, decide what are the useful templates that the organization should offer, and then sets up policies so that individual users are able to say, first user may be able to instantiate a single VM but not a cluster. A PI may be able to do a cluster directly. And then you basically turn the research community loose, and you give them the ability to self-provision these, these virtual clusters and virtual machines for themselves. We also, and from a product perspective, from a VMware perspective, this would be using, for example, vRealize Automation, which is a private cloud offering that we have. This is all built on vSphere, which is the virtualization platform, and vCenter, which is the management platform. Bursting out to hybrid and public cloud is possible, but the basic idea here is that these research clusters are being spun up dynamically using whatever software stacks the individual research teams require. And it can be done at this level directly by the researchers using the self-provisioning capability. Now, the other thing that is a current work in progress at VMware is adding another layer of abstraction on top of that. And this came about through discussions with folks at UC San Diego, who are working with researchers that would prefer to not have to deal with Linux instances and clusters and whatnot. What they really want to be able to do is talk about analysis pipelines. They want to be able to say, here's this appliance. This appliance encapsulates some sort of life sciences workflow. I don't want to understand the details. I don't want to understand whether it's made up of a single machine or multiple machines. I just want to use this. So the idea is that a researcher publishes one of these, what we're calling recipes, and then other researchers can come along and basically attach their own data sets to that recipe and have the results generated. So the idea is to move up in a level of abstraction and ultimately to make this a multi-university collaboration tool so that it's possible for recipes that are generated at one site to automatically migrate to another site and then be invoked on data sets locally there. You'll notice, as an aside, that I'm also showing you an OpenStack-based solution here. VMware does support an integrated version of OpenStack with OpenStack on top with our hypervisor underneath. That's certainly a possibility for virtualized HPC environments. Okay, let me quickly go through some performance. And the idea here is to show you basically head-to-head comparisons between what we have on the left-hand side, bare metal, just running in a Linux instance versus running that exact same operating system and application, but running it in a virtual environment. And I'm just going to go through these relatively quickly. What these are showing you are the ratio of virtual to native performance, so virtual to non-virtualized performance as a ratio. Higher is better. If we're at 1.0, that means we're delivering exactly the same capabilities. Sometimes you'll see us a little bit above 1.0. Sometimes you'll see us below. So we're looking at BioPerf here, which is a pretty well-known benchmark suite. And you can see that we're doing very close to native on all of these. We also looked at BLAST, and here we're looking at the ability to handle multi-threaded jobs. So as we increase the number of OpenMP threads from 1 up to 16 here in this particular test, you can see that we're able to maintain very good performance relative to native. There's really no degradation here. And as Sasha said, there are misconceptions out there about virtualization and in particular with respect to performance. It's really not the case with modern hardware with its acceleration of virtual infrastructure and with the virtual infrastructure itself and the sophistication of it, that there is extra software really sitting between your compute-intensive application and the underlying hardware. It really does run very close to full speed. Moving on, Monte Carlo, also a very important algorithm within many of the sciences. This happens to be a financial services example, and what we're seeing is pretty much dead on exactly the same performance running in bare metal and on our hypervisor. Now, I do want to speak, I know there's a lot less MPI in the life sciences than in other parts of HPC, but I do want to at least briefly mention that if you look at the latency overheads on the platform with respect to, this is FDR InfiniBand, you can see there's a close-up on the right-hand side of what I'm showing on the left-hand side. You can see that the green line is, the red line is showing basically what native performance is, unvirtualized. And the green line is showing our current performance on a ping-pong benchmark, and we're looking at microseconds here. So this is about a 0.3 microsecond difference here on the right-hand side, 0.2 to 0.3. That's actually, turns out it can be pretty significant in terms of its effect on MPI applications. But I will call your attention, it's maybe a little bit hard to see if it's small for you. But the, excuse me, the blue dots here are showing you what our latency, what our performance is on an upcoming version of the hypervisor. And basically what it shows is that we've completely eliminated the latency overheads for InfiniBand on the platform. But having said that, I'm going to flip through a few additional slides. These include that overhead that I just mentioned. So I'm not showing you the data with the latency overhead removed. But here's NAMD, and what we're doing is it's running on an 8-node cluster, and we're scaling the number of MPI ranks from 8, that's NP8, up to NP128. And you can see for these 3 different models, we're holding pretty close to 1.0 for NAMD. We also looked at NW-Chem, and here's an odd case where we're getting at the NP16, we're actually doing a bit better. We're doing better than native. We haven't really examined that, but it's not 100% surprising to us. But again, we're doing quite well. And then the last one I wanted to show you is lamps, at least on the InfiniBand side. And here, I really want to make the point, we are seeing a fall off here at 128 relative to bare metal. We're down to around 70, I think 77% here. And the point I want to make is that I'm not saying that all MPI applications run without degradation on virtual platforms today. It really does depend on the amount and the particular characteristics of the messaging that's happening. And LAMPS happens to do quite a bit of small messaging as the number of as the ranks increase. And so it's important to remember that point. And I just briefly, as the last performance slide, just want to mention we also spend a lot of time looking at Hadoop, which we know is important in the life sciences and other parts of HPC as well as the enterprise. And what we're looking at here, again, is ratios between virtual and native. And you can see we actually have a fair number of these data points that are actually above 1.0, meaning that we're doing better than native. But the real takeaway here is that you can run Hadoop in our virtual platform with really no degradation in performance. This is done with local disk and with 10 gigabit. It's not using InfiniBand. And then the last point I wanted to make before wrapping up is that we are also able to run accelerators in the environment. So we've looked at Intel Xeon Phi. I don't really have time to go through the graphs in detail, but what the graphs are showing you is that the performance is virtually identical, bare metal and virtual for Intel Xeon Phi. Our initial GPU results on NVIDIA were promising. I have an intern in the summer who's about to start looking at one of the newer NVIDIA cards, and I'm also getting an AMD card that we're going to be taking through its paces as well. But I expect that the performance there will also be very, very close to bare metal. So summary, so performance, first off I would say performance has changed hugely over the last, say, 5 to 10 years on the virtual platform. And old data is generally very, very inaccurate data. And I hope I've shown you today that a wide range of science applications, certainly around the life sciences, can run with little to no degradation on our virtual environment. As I said, the throughput applications, they usually run under 5%. It usually tends to be a couple of percentage points. In MPI, it matters. It depends a lot on the messaging characteristics. And then the bottom line really is that virtualization and cloud technology, they really do bring a degree of flexibility and new capabilities into science environments that, while still delivering good performance, that we think is worth taking a look. We have a lot of customers that are looking at this right now. It's still very early days for this. We have a relatively small number of deployments, but the interest level is really cresting at this point, I would say. It's really quite high, and a lot of that interest is coming directly from the life sciences. And I'll leave you with a couple of additional slides with pointers to resources that will tell you more about virtualization and high-performance computing. And with that, I'm done, and I'm happy to take questions.
All right, thanks. Josh, thanks for taking us through, really sort of the arc of, bringing really together a variety of different resources that could be, across the different departments in an organization, and then, pointing out how a scientific cloud could be stood up, and then through the performance measures that you just shared. Earlier you actually mentioned a few other industries like financial services. So in terms of a question here, are there any other, beyond life sciences and say financial services, are there any sort of best practices or recommendations when it comes to other industries? Maybe, for example, like EDA kind of comes to mind. Can you share any thoughts in that direction?
Oh, absolutely. So I would say the single most important thing to realize is that our platform in particular, because it's targeted so squarely at enterprise environments, is really out-of-the-box tuned for throughput as opposed to latency. And latency plays such a critical role in the HPC environment. And that could be NUMA latencies if you're looking at what's going on chip. But it could be I/O latencies. So, for example, getting to your network-attached storage, you're going over a network link. Latencies can definitely have an effect there. So the most important thing, regardless of the area of HPC that a person is working in, is to apply some level of tuning to the platform, not to the application, but to our platform itself, in order to mitigate the effects of latency.
Got it.
And I would say, actually, there is a pointer in the document there, in the list of resources, to a latency tuning white paper that covers a lot of those issues.
Yeah, and in fact, kind of along those lines, I had taken a peek at that particular paper and kind of came away with the impression that when you move in this direction to set up a virtualized HPC, there is some degree of tuning that IT managers, HPC administrators will probably need to do. And I'm kind of curious, is VMware planning to introduce any capabilities to sort of automate some of that tuning and make it easier for groups or individuals to stand up a virtual HPC?
Yeah, that's actually an important thing. So for VMware, we really want, generally speaking, we want customers to have a good out-of-the-box experience with the product. And so it's really the fact that HPC is still relatively new to the company that really requires this additional tuning. Over time, that will become more automatic. We have and semi-automatic, I guess I would say. We've added a capability into a recent release of the product that basically lets you go in and say, this virtual machine is going to be running latency-sensitive workloads. And once you say that and tell us that, we will take action and apply some amount of that tuning that's in that white paper automatically to that virtual machine. Not all of them, but over time, I think that will become a more comprehensive capability. But you're right, it has to be made more automated.
All right, there's actually two related questions here from the audience, and I'm going to take the one here. I think that's probably the broadest, but will encompass both questions. And the question starts here. It says, are there any policy hurdles that you are encountering as you attempt to have these systems broadly adopted by the HPC community, whether that be federal R&D requirements or research community best practices? So, and the other one is kind of related to auditing and logging, in say, a regulated environment to adhere to, say, FDA requirements. So, I think these two questions point to more about data governance and governance in terms of auditing and logging. So, Josh, have you, in terms of working with different organizations, what do you see there in terms of governance?
Yeah, so somewhat early days for us. The discussions that we've been having with San Diego, with UC San Diego, they've mostly focused around things like HIPAA compliance. That's been the main issue for them, and so we focused on that. And there are other compliance and security things like FISMA that we've looked at as well, but that's going to be definitely an evolving story for us. And I think for example, the UCSD work is really ultimately targeted at moving kind of up level to getting the attention of NIH and moving more broadly. And I suspect once we do that, then more of these kinds of issues are going to come up. But as of now, it's been mostly questions from customers around things like HIPAA. The other things, from a policy perspective that we run into, it's not exactly what's being asked, but there are. So this idea of centralization and pooling resources seems to be somewhat difficult for some organizations to adopt, really, at least partly because of the funding model and the granting models from the government, where there are some level of discomfort perhaps in pooling resources that are coming from, in pooling money that's coming from different grants and putting that into centralized resources. We've run into some organizations that are doing that, feel comfortable sort of pushing the envelope on that, and others that have not. But that seems like something that needs to get knocked down, because it's a win-win for everybody if more resources can be used more effectively.
Got it. All right. I see now we're actually two minutes over our time, so I think this is a good place to conclude. Josh, again, I want to thank you for taking time out and be part of this webinar series that we've put together.
My pleasure.
I will now, I guess, hand it over to Morgan to close us out.
Great. Thanks, Sasha, and thanks, Josh. That was some great information today. Thank you to our audience for attending this Fierce Live webinar and for submitting your great questions. I'd like to again thank our speakers for participating and EMC for presenting today's webinar. The webinar has been recorded. You'll be able to access the recording within 24 hours on the same page that you used to register for the event. So thanks everyone again for joining, and we look forward to seeing you at future events.